Kia ora koutou, ko Douglas Walker, tōku ingoa. I'm here tonight with Andrew Sargent, who you'll have seen in some of our previous webinars, especially if you're on last night for the mechanics stream. Tonight we're going to be focusing on the level 3 electricity standard, and then we'll have a wee gap and we'll move on to waves. Andrew is currently the head of science at Takura and has many years of experience teaching in physics. If you've got any questions throughout the stream, just pop them in chat and Andrew and myself will monitor those and do our best to answer those questions. And if you come up with some questions later, head over to the Study It forums and pop those questions in there. And again, a very dedicated team of teachers will do their best to answer those questions before your exam, which is on Thursday. Yeah, I don't think there's anything else I need to say there other than thank you to Study It for sponsoring these webinars. And over to you, Andrew.
Kia ora tātou, ko Andrew Sargent, tōku ingoa. So today we'll be going through the level 3 electricity, and then the next stream at 7 o'clock we'll be going through the level 3 waves. Just looking at the chat, is anything on for tomorrow? No, we'll just be doing so we did the mechanics last night, the stream, and then you can just, I mean, Doug can link that in the chat. And then today we'll be doing the electricity and the waves. So I thought I'd go through, I just need to share my screen, don't I? Yes, I do. Where's my Zoom? There we go. Share screen. Screen one, there we go. Sweet. So I have linked the folder in the description of the video. I might actually just chuck this in the chat while I'm here. There we go. So this is the PowerPoint I went through last night, but I added a few. Well, I actually just added one thing. So I've added down the bottom. Someone asked a question about phasor diagrams for simple harmonic motion. I've added in a simulator so that you can just have a play around with, and it pretty much just it's self-explanatory how the sort of phasors work. You just play around with it and you'll get an idea of what's going on, and it physically represents what's going on. Like the phasors, graphically represent the physical goings on of a spring. So it's quite intuitive once you sort of have a play around with it. Right. So on to exam strategy. This is just going to be a repetition of yesterday. So set a minimum of 2 exams, take the KDR approach. So if there's any questions that you get wrong, try and do at least 2 or 3 types of the same question until you're like familiar with it. You can also have a look at like previous exams to see whether some questions are more common than others. But it's really hit or miss. In like any exam, you will not get all the content. So for every like exam, there will always be questions that you won't get. So you might have spent a lot of time practicing, I don't know, capacitor decay graphs for voltage, maybe. And the chances are it might not actually even be an exam. But you don't know that, and there's nothing really much you can do about that. So you can't really game the exams in that regard. You have to sort of know everything. There are some sort of, the best approach is just practice previous exam questions. Right, so go down to electricity. So it's split into 4 separate areas. AC circuits is kept for the most part distinct. So most AC circuit questions are separate from DC circuit questions. They're quite separated. All the rest, so the capacitors and DC circuits, inductors and DC circuits, resistors and DC circuits, they can be all like muddled in. So they're not ever like distinct questions. And if you know what if I go down to the next slide, you'll see internal resistance was asked 2014, 15, 18, 19, 20, 21. Kirchhoff laws. You do not need to know how to do simultaneous equations for Kirchhoff laws. They're just like simple linear equations that you'll get given, but it pays to know how to do this, and it pays to know how to use this approach because this approach can be very handy for just about all of the DC circuit questions. Capacitors and DC circuits, right? I've split it all up, but you can see like most of the questions don't come up that often. They're not like it's luck of the draw what you get really. Right, inductors and DC circuits here, you can see I've all split it up. AC circuits, I tried to split things up a little bit more in terms of like peak RMS and current, voltage, current, the phase relationship. I haven't really, I did actually put phasor diagrams in, and then resonance as well. So resonance in LCR circuits is typically always an excellence question. So yeah, you can see it's 3D, 1D, 3D, 1D, 3D, 1D, 1D. So it pays to know how to answer one of these questions because it's always not exactly an easy E, but it's an excellence that's something you can somewhat memorize without having to know that much detail about it within reason. Right, I think that's it. Right, so today I'm going to go through the 2013 Waves exam. The reason for that are all the other exams from 2021 down to 2014 already have exam videos on them. So if there's something that you don't know how to do, like if there's some specific thing that you have no idea, maybe you don't know how to do phasor diagrams, just go to like phasor diagrams and then see that, okay, 2014, maybe not 2014, 2015 question 1C, just YouTube that on my YouTube channel or on Mr. Wibley's YouTube channel, and you'll be able to find a video walkthrough. Although Mr. Wibley only goes down to 2019, I think. He doesn't go down to 2015, so I think he might have started teaching a little later than I did. Right, so on to the past exam for today. I need to actually go up to the next tab. Electricity. Sweet. And I'll quickly go present. And I need to change some settings. There we go. If you do have any questions, you can just post them in the chat, and I'll try and answer them. Right, so I thought for this sort of tutorial, every question that we get, I'll go and explain sort of what the question's about. So straight off the bat, looking at this is a DC circuit question, and it's a DC capacitor circuit question because I have a capacitor here. I've got a little bit of internal resistance as well, so it's going to come under the topic DC, a little bit of internal resistance, capacitors and DC circuits. So I'm possibly going to have to be looking at voltage, charge and discharge, or maybe charge, discharge and discharge for a capacitor. Okay, there's a bit muddled. So I could be possibly looking at discharge and charge graphs for a capacitor. I've got a lamp here, which will probably maybe get you to ask what happens to the lamp. Maybe. Right. So I'll just you can read question 1, and I'll just read it quietly. So you can pause and read question 1. Right, so it's asking, hopefully you had a read, calculate the charge stored in the capacitor when it's fully charged. So when the capacitor is fully charged, its voltage, when switch 1 is closed. So switch 1 is closed. Again, I'll explain the complicated bit soon, actually. So switch 1 is closed, switch 2 is open. So the lamp's not really doing anything. So when the battery is going to slowly charge up the capacitor, the current in the circuit in this top loop will slowly decrease until the capacitor is fully charged. When the capacitor fully charges, it'll be at 12 volts. So the capacitor will be at 12 volts. Cool. If however, the second switch was closed, the capacitor would not charge up to 12 volts because there would always be current flowing through that little resistor R. And that means that little resistor R would have a voltage across it, which means the voltage across the capacitor would be 12 volts minus the drop across that little resistor. So this is how you could turn this question from a simple achieved to an excellence question. And that's that component would throw up a lot of bits. Right, so back to question 1, calculate the charge stored when it's fully charged. So in your formula sheet, I might actually open it up. I'll actually show you what the different formulas are. Wrong screen. Ooh. There we go. And sweet. So my pen didn't work. No, it didn't. I can actually comment. I'll open this up because I'm going to use this for later anyway. Hopefully this hasn't crashed my computer. Maybe it has. Right. So I imagine you can. Oh no, there we go. It's working. Cool, we'll move that out of the way. So this is the formula for the charge stored up on a capacitor. The top line is pretty much, well, this is a capacitor. This is the energy stored in a capacitor. Here we've got capacitors in series. Here we've got capacitors in parallel. We've got the formula for the capacitance of two plates. So if you're going to build a capacitor and you're going to ask yourself how much capacitance would it have, that's how you calculate it out. For inductors, there's no formula to work out the inductance of an object given its shape. That's mostly just witchcraft. The way that you actually measure inductance of inductors is you run AC voltage through it, and then you measure its reactance at different frequencies. Here we have the voltage across an inductor, etc. So we'll go back to that question. So we're going to have the charge Q is equal to CV. We have the capacitance, it's 125 microfarads. So we're going to have 125 times 10 to the negative 6. That's the capacitance. And we're going to times that by the voltage when it's fully charged. That's going to be 12 volts. 12 volts. And that is going to be equal to, and I'll actually use my calculator just because I can. Menu 125 e to the negative 6 times 12 equals, so it's 1.5 e to the negative 3. So we're going to write, and there we have how many significant figures? 3, 3, 3, 3. So it has to be done to 3 significant figures. So we'll write 1.50 times 10 to the negative 3, and it's coulombs because it's a measure of charge. Is there a distinct difference in the 2000 exams to what we get nowadays? Nah, the only thing that's really changed is the mark schedule. All the content's pretty much the same. In fact, yeah, this type of question is actually just a good question to ask. So maybe if I was to write an exam for 2022, I just swap that capacitor out for an inductor. So this is a pretty bog standard sort of question. There's not really much difference, except for I think the old exams go down to like 1 to F, whereas the 2021 and 2022, the last 3 years only go A, B, C, D. So they go down to F. Right, so we got question 1. The internal resistance R of the battery is 1.8 ohms. Explain why the charging is almost instantaneous. So if you go to your formula sheet, you'll have a formula. Tau is equal to RC. So this is what's called the time constant. And the time constant is it's essentially how long it takes to charge the capacitor. So one time constant, hold on. So if switch 2 was closed, would we minus the R voltage or the 128 ohm lamp? So you'd minus the R voltage because the lamp would be in parallel with the capacitor. So if we remember from year 12 physics, components that are in parallel with each other will always have the same voltage because you could do a closed loop in that parallel section. And if we remember Kirchhoff's voltage law, in any closed loop, the voltages will sum to 0. So that's how we'd work out that. Right, so where was I going with this? After 5 time constants, the capacitor can be considered fully charged. And then after 5 time constants, the capacitor can be fully discharged, whether you're charging or discharging. It depends on whether you're charging things up or not. So here we have tiny capacitor, and the resistor is 1.8, so that's also really tiny. So I actually pre-wrote this answer so I can save myself some time. So the capacitor takes roughly 5 time constants to become fully charged. And I've written the formula. The time constant is equal to the resistance times capacitance. As a resistance, I wrote the little capacitance as little c. It should have been big C, but whatever. As a resistance capacitor low, and it pays to calculate this out. So I've got 1.8 ohms and 125 microfarads. It'll take 0.1 milliseconds to charge. So there's one other thing I can probably add. So the voltage decay formula for a capacitor, so the voltage that you get is equal to the initial voltage times e to the power of negative, and then this is time that's elapsed, is in like seconds, so I don't know, maybe 10 seconds, 30 seconds, whatever you want to put in, divided by the time constant. So this is in some textbooks. I know it's in the Boltzmann textbook. I don't know if it's in the AME textbooks. The reason why I'm mentioning this is because if you have 5 time constants, so let's say the time constant is 1 millisecond, 5 of them is 0.5 milliseconds, then you just end up with e to the negative 5, because you'd have 5 time constants divided by a time constant, cancels out the number, and you get the ratio. So e to the negative 5, if you do that on your calculator, that is very close to 0. The other version of this is for this is the decay version. If it's dropping away from its max voltage, this is the charging one. So if it's charging up to a max voltage, it's equal to V naught. Then it's 1 minus e to the power of negative time over tau. You can just do we have to state the 63 and 37%? Not for this question, because this is just asking when it's fully charged. So after 1 time constant, if it's charging, it'll get to 63% of the voltage. If it's discharging, it'll get to 37% of the voltage. But they're only really, there'll be a question after this, I can imagine. Is there? Possibly. Let's go. I dare say we'll probably get to that soon. Switch 1 is open, switch 2 is closed, so the capacitor discharges through the lamp. On the graph below, mark the values on the axis and plot curve with at least 3 points to show how the charge on the capacitor changes during the discharge process. So it's going to start at max charge. So what was the max charge? Max charge was 1.5 times 10 to the negative 3. So we're going to have that at the top here. 1.5, and I'm just going to leave. I'm going to put the times. I should have actually. I'm going to write that out. Can I write that out? I am. So I'm going to put times 10 to the negative 3 over here, and then I'm going to put 1.5 here. And then I'm going to put the units as well, because this is coulombs. So it is capital C. Okay, that kind of looks funny. C inside. It looks like the copyright symbol. So that should be 1.5. And it's discharging. So it's the graph is going to look a little bit like that. After 5 time constants, so I'll put, how do I want to scale this? The time constant's changed as well. So I'll quickly calculate the new time constant, because it's now going through the lamp and it's not going through that little resistor. So the time constant, does our graph have to be neat and tidy? Preferably, but it doesn't. It doesn't actually have to be. If you only really get marked on the points per se. So I'll elaborate on that a little bit soon. I'll just calculate this time constant. The time constant is the resistance times capacitance. It's going to be 128 multiplied by 125 times 10 to the negative 6, and I'll quickly work that out. I'm going to do that. Do that on my other calculator. So we're going to go clear that. 128, because that's the bulb resistance, multiplied by 125 e to the negative 6. Yes, and we got 0. What was that? 16, wasn't it? I shouldn't have made that go away so quickly. 0.016. 0.16. So that's 1 time constant. So I might. What might I do? Make everything down the bottom times 10 to the negative 2 to make things a little bit easier for myself. So I have to write 2 extra zeros. So down the bottom is going to be times 10 to the negative 2. So maybe here I'll put 1.6. Scale doesn't matter. So it's going to be 1.6. Double that is going to be 3.2. I'm going to have 5 time constants. 1, 2, 3, 4, 5. Okay, the 5th one's going to be kind of off the graph. Whoops. 32 plus 16 gives me 48. There's going to be 4.8. 4.8. I would highly recommend not doing what I'm doing, because I'm doing it in my head. You've got a calculator in front of you in the exam. I'm just trying to save myself a little bit of time for this tutorial. 48 plus 16 gives me 62. Yeah, it does. Hopefully that's 62.6. That's 6.2, 6.2, and then 7.8. So 7.8 will be down here somewhere. 7.8. Right. You only need 3 values for the charge to get merit or excellence. Often this is either a merit or an excellence question. It sort of depends on the year. this will probably be mirror. It'll definitely be mirror. It might be, it could, like, from this year, it is definitely a mirror. I'm pretty sure. Actually, I'm gonna go check. I know. I'm pretty sure it's a mirror. You can look this up. You got the answers. Right. So we need to go 1.5, and we'll times that by 0.63%. I'm not going to use the complicated formula just because I know 90% of you have probably been taught just the 37 and the 63% rule. So it's probably easier to do that way. So 1.5, and now we're decaying. So we're going to multiply that by 0.37 because we've dropped 63%. So we're down to 0.55. So I need to actually quickly, half of 1.5 is 0.75. So this here, that there is 0.75. I'll go back to my calculator because I forgot what that was. 0.55. So we're down here somewhere. Half of 0.75 is 37.5. So here we have, I think it's 37.5. Clear. 75 divided by 2. Yeah, 37.5. So it's down here. 37.5. So at one time constant, which is 1.6 milliseconds, I think, or 1.6 times 10 to the negative 2, that should be a negative 2, by the way. I'm going to put a negative 2 there. They will they ask us to plot the graph for current against time constant? It'll be current against time. Maybe, yeah, possibly. Yeah, it really depends on the question. Here they're asking charge. They could have asked current, or there'll be the exact same process. We'll just find whatever the max current is, and the max current would just be well, the voltage across that the capacitor will be 12 volts. So you go 12 volts divided by the resistance that it's going through, and that'll give you the maximum current. And then as the voltage would drop, obviously the current would drop. Because that's just Ohm's law of equals IR. It'll be the exact same process. So we're going to go, I think we're going to point at 0.55 somewhere down here. So here's our 0.55. When you're doing this, you should probably put T1 0.55 coulombs. So you can show you're working to T2. T2 is equal to, and you should possibly work out the time constants as well. So you'd have T1 is equal to 0.016 seconds. T2 is equal to 0.032. That should be a 3, by the way. 2 seconds, etc. So show all your working. That way, the examiners can sometimes be a little bit lenient. If it's not super obvious where you put the data points, but try and be neat about it. And then we're going to go 0.55. We're going to times that by 0.37 again because we're going to drop again. So we're going to times 0.55 by 0.37 because we're going to decay again. So we're down to 0.2, which is about here somewhere. Oh, no, what happened there? Which is about here somewhere. About 0.22, I think. And then you've got the original one up here. So that is enough to make a graph. Typically, you only need 3 values according to just about every mark schedule that have gone across. When you do this, obviously, just do all the values, calculate the 4th value. You just go that 0.22 and then times it by 0.37 again, and then you put in wherever the dot is, wherever the input across. Not just like a messy thing like I've done. And then the 5th time constant should be very close to 0, but not exactly 0. So that's for that one there. Right. So the lamp will glow at normal brightness if the voltage across it's between 9 and 12 volts. Use the graph to estimate the length of time that the lamp will be glowing at its normal brightness. Okay, so this is where you probably should have been a little bit tighter than what I've been. But we might be able to estimate it roughly. So what we want to do is find the charge at 9 volts. So we've got Q is equal to CV. And it's just going to be the same capacitance. So 1, 2, 5 multiply times 10 to the negative 6, 10 to the negative 6, and then we're going to multiply that by the lower voltage of 9 volts. Because what I want to do is I just want to find the lower charge value, and then I'll just go to my graph, figure out where that is, go across and go down, and that'll give me my time. So that'll give me, I'll do that on my calculator. Clear, 1, 2, 5. e to the negative 6 times 9, and that's going to give me 1.25 times 10 to the negative 3. So that'll be 1.25 e to the negative 3. The scale here is, so that's going to be 0.75. That'll be about here-ish. Here-ish. So we'll go down to here. So it's definitely going to be less than a time constant. So that's probably going to be about half of 1.6 is 0.8, maybe about 0.7-ish seconds. So we're getting about 0.7. So 0.7 times 10 to the negative 2 seconds. Yeah, and because it's starting at 0, it goes to there. I'll quickly check the chat. I better actually check the answers to see that I haven't made any negative 2. So the answer's got 0.56. I'd say if I was a little bit tidier, probably would have been a little bit more accurate. Another way that you can possibly do this is using the exponential formula up here. Where did I put it? Using this formula here and rearranging for time. That's another way that you could do it. You'd start off with, you'd have your V is 12, your V naught, your V is 9, your V naught is 12. You'd put the time constant in and you'd rearrange for T, and that would give you the exact answer. So that's another way that you can sort of cheat your way around having to use a graph. Right. Second, ideal capacitors connected in series, one shown above, show the total capacitance, total capacitance of the two capacitors in series is that. So when you have capacitors in series, they add like resistors in parallel. So it's just going to be two, like one. It's going to be 1 over 125 times 10 to the negative 6 plus 1 over 125 times 10 to the negative 6. And then that's going to be equal to 1 over the total, like the total capacitance. Thing for like a wee shortcut for this is you have two identical resistors in parallel. Their total resistance is exactly half of whatever the sticker value is. Same applies for two capacitors in series. So if you two identical capacitors in series, the total capacitance across them is just going to be exactly half. And you can sort of see exactly half of 125 is 62.5. So this is a show question. So what I actually should have had is I should have had the 1 over C1 plus 1 over C2. Oops. So for show questions, you must have the formula, the working, and then the answer. So we can say, I'll just actually rub this out. CT is equal to 62.5 times 10 to the negative 6 farads. Yeah, I was a little bit naughty with this, making it super messy. Yeah, if you're not writing with a stylus on a page or on a laptop screen, it makes it a little bit easier. So for show questions, you have to like write what you're doing. Next question: explain using physics principles the effect new capacitor arrangement on the time constant of the circuit. So you decrease the capacitance, you are going to decrease the time constants, because the time constant is just equal to the resistance multiplied by the capacitance. And I've pretty much read that answer. Yeah, adding capacitance series decrease total capacitance as the capacitance is decreased, so will the time constant. So that's just an achieved question, that last question, because it's a fairly straightforward sort of question. It hasn't explained there's not really much more to it than that. Right. Next question. So I'll just you can pause, have a read through it, and then I'll start on question 1. Right, so this is an inductor in DC. So that's the type of question it is. The inductor's got a little bit of internal resistance, so it's not an ideal inductor. You've got a spark gap down here. So anytime you have a break in a circuit with these two little boxes, they're always spark gaps. And you can just about guarantee that it'll be asking you something to do with this. Either it'll be like a spark plug or whatever, really. It could be a barbecue lighter. Were any of those last ones excellence questions? I'm going to actually double check that. I'm pretty sure, obviously, one of them has to be an excellence question. It was question D. So question D, we had to estimate, if I go back up to here, this one here was an excellence question. So just using the graph, like obviously more accurate than what I've done, just getting this answer here was an excellence question, which is actually reasonably straightforward, quite a few steps to it. And there's a few like ways you can make a mistake, such as what I've done by making it too messy. So when you do your graphs, try and make them a lot tidier than I have. But the process is still exactly the same. Right, so question A, calculate the energy stored in the inductor when the current's risen to the maximum value. So if I get the formula sheet, the energy stored in an inductor is equal to half the inductance times the current squared. There we go. So that's the formula there. I've just circled it. I'll just move this back into the... and also inductors store their energy in magnetic fields. Capacitors store their energy in electric fields. So that's another thing to distinguish between. Sometimes there's questions on that. It's not a very common thing to ask, actually. Yeah, it's not very common at all. So we'll write that out. This isn't a show question, so we don't actually have to show any working, but you should. Half Li squared. We're going to have half 0.51 times 1.7 squared. I've left the extra significant figures out because I'll do that at the very end. So I'll grab my calculator. Clear 0.5 times 0.51. There's no zeros in there. Times 1.7 not e to the 2 squared, and we get 0.73. What was the rest of that? I can actually look at my screen and find. No, I can't. 7369. 69. So round this up to 3. Yeah, everything's done in 3 SF. So this is rounded up to 3 SF. So the energy is equal to 0.737 joules. There we go. Calculate the value for R shown in the diagram and explain its effect on the maximum current. So this is like a fairly straightforward Ohm's law question. So you've got 120 volts running through that resistor. It's got the resistor is what's throttling the current. So this is after the circuit is at steady state. If the circuit was not at steady state, so maybe if they asked this question with regard to after the inductor had been charging to one time constant, then it would be a little trickier because then what you'd have to do is you have to work out the voltage across the inductor, which would be, well, if it's charging up to one time constant, it would have increased by 63%. So it'd be the inductor's voltage would be 63% of the supply. So whatever the supply is 120, so 63% of that, and then you'd use a Kirchhoff loop where you'd go the 120 volts minus the opposing voltage, because the inductors always oppose the supply, so it'd be minus that 63% of 120, and that would give you the voltage across that little resistor, and then you'd have to. You wouldn't be able to figure that out. Actually, you would not be able to figure that out. So they'd probably give you maybe the resistance, and they'd ask you to find the resistance. Yeah, would they give you? Yeah, they'd give you the resistance. Okay, it's not a question you could ask. I was trying to think of tricky questions you could ask, but no, I think that you couldn't actually do that. Right. So we'll quickly just do this. 120. It's not a show question, just divided by the current. 1.7, and it's just because V is equal to IR. So I've gone voltage divided by the current gives me the resistance. So that is going to be equal to clear 120 divided by 1.7 gives me 70.6 ohms. Yeah, so 70.6 ohms. Right, well, you see the answer anyway. Explain the effect of the inductance on the time it takes the current to rise from maximum value. So I'll just show the answer that I had. So when you first flip the switch, there's a large change in current. This induces a voltage across the inductor, which opposes supply and voltage. And then I put the formula for calculating the voltage across an inductor with respect to the rate of change of current with time. And then I've said this opposing voltage decreases the current in the circuit proportional to the rate of change of current. As the current builds up, the rate of change decreases, so the induced inductor voltage decreases, leading to more current flowing. That is one way you can answer this question. The other way you can answer this question is with regard to the flux across the flux through the inductor. So the other way that you could explain this is to say when the switch 1 is first switched on, and like this is assuming the inductor is uncharged, the inductor will have a large change in flux across it because there is a current, like a large current flowing through it. This large change in flux will self-induce voltage, or will induce a voltage across the inductor, which will oppose the voltage that was used that supplies the inductor. As the change in flux decreases, the opposing voltage of the inductor, or you can say maybe the back EMF of the inductor, decreases and the current slowly rises to maximum. So that's the other way in terms of change in flux. Really sort of depends on the year. Sometimes it pays to sort of give both explanations. But I would argue both of those explanations are probably fine. You shouldn't really get the mark for either explanation, because both of them, for the most part, both of them do explain why that's the case. Cool. Right, switch 2 is closed in addition to switch 1. So you got a break in the circuit. Here's the break. If you close switch 2, nothing happens. It's just a short circuit. That inductors only produce really, really high voltage sparks when they are in a circuit where there's a really short time constant. Because switch 1 is still closed, the time constant of the circuit is still quite low, and it's still quite high, I should say, because you've got this little internal resistance here. So remember, just the time constant for an inductor is equal to the inductance divided by the resistance. So when you make the resistance really, really large, then the time constant gets small. But in this case, it's a very 78 ohms or 70.6 ohms is actually still quite small in the grand scheme of things. So nothing happens, current won't flow. Hold on, wait. Explain what happens to the voltage across the inductor. Yeah, nothing. It's a short circuit, so the current won't flow. I should have added the current won't flow through branch 2, so it won't affect the voltage across the inductor whatsoever. However, when you open switch 1 and close switch 2, so here we have this now becomes opened, this now becomes closed. We have a closed loop around here, and the AB. So there's like a running joke that everything will conduct electricity if the voltage is high enough. I don't know if that's a joke, but something I used to tell my students: everything will conduct if there's a high enough voltage. So even air is like a conductor. It's just a really poor conductor. It's non-ohmic, so funny stuff happens, but it just has a really, really, really high resistance. Because it's got a high resistance, it means this circuit here now has a really, really short time constant. Because it has a short time constant, you're going to get a really like a short change in current, or like the current is going to bang straight away to 0. And if you remember from this formula here, E equals change of the inductance multiplied by the change in current over change in time, you can get extremely high voltages. That's one way to explain it. The other way to explain it is with regard to the change in flux. So the voltage induced when you have extremely high change in flux can also be really high as well. So if we go down, I'll show what I put. So the gap AB is considered non-ohmic resistor with really high resistance. It's now in series with the inductor, which causes the circuit to have extremely high, a very short time constant. You can probably calculate what that is. I know you couldn't actually, because you don't actually know what the resistance of that spark gap is, of that like air gap. So yeah, with a very short time constant, the inductor's collapsing magnetic field will induce a very large voltage. You could also use, so this voltage will be high enough to cross the gap. Where's the formula sheet? This formula here So that's Faraday's law, or Faraday's formula. So the EMF is equal to the negative change in flux over the change in time. Because the magnetic field in the inductor is collapsing extremely quickly, you're going to get a massive change in flux, and also with another very short change in time, because the time constant of the circuit is very low. So these two things coupled together will give extremely high voltage. Right, I think I've said enough on that question. Right, last question. This is an AC circuit question because you've got a little squiggly sign for the voltage. It's given all our voltages and RMS values, so that is cool. You can either calculate everything in RMS or you can calculate everything in peak, but you cannot muddle the two. So if you've got something that's a peak voltage and an RMS current, you can't use like Ohm's law together. You can't go that voltage divided by that current. That'll just give you nonsense. You have to either convert the current to peak or the voltage to RMS. Hopefully that makes sense. I just think that I might have muddled that a bit, but yeah, hopefully you get my drift. So reactance of a capacitor at this frequency, the formula for reactance. So reactance is essentially like the fancy resistance. That's usually what I call it. Probably physics teachers are turning the grave at that, but it's an easy way to explain it. So the reactance of a capacitor is equal to 1 over the angular frequency times the capacitance, and that is just equal to 1 over 2 pi f times the capacitance, and I can show you where this is on the formula sheet. Here is the capacitor. Here's the inductor, and you'll notice that the reactance of a capacitor and the reactance of an inductor are inversely related. So as the frequency goes up, the reactance of a capacitor goes down, and for an inductor, as the frequency goes up, the reactance for an inductor increases. So, and if you know about, well, we'll get to this soon actually, I won't talk about it just yet. Right, so we'll quickly calculate out what this is. So we have 1 divided by brackets 2 shift pi multiplied by the frequency. What is the frequency? 450 hertz. Says it up here. 450. I'm not going to highlight that because I'll lose my mouse. 450 hertz. And then we're going to multiply that by the capacitance as well. And the capacitance is 15 microfarads. 15 e to the negative 6 bracket. 23.6 ohms. 23.6 ohms. So reactance is just a measure of resistance. But unlike capacitors in DC circuits where they just charge up and stop, capacitors in AC circuits, because the voltage is constantly flipping back and forth, they will react to the circuit. Right. Next question. Okay, I'll just go. The total impedance of the circuit is 93 ohms. So we have Z. Z is 93 ohms. Is that all we've got? Yeah, that's what we've got. We've got the resistance. We've got the capacitance, the supply voltage. I think that's really pretty much all you need to work out everything else. So if the supply voltage leads the current by an angle theta, calculate the value of theta. So for the phasor diagrams, like the generic phasor diagram is the. Do we want to do the voltage? No, we'll do the reactances. So the inductor reactance leads the resistance by 90 degrees. So here's the resistance. The resistance is in phase with the current. And then we have the capacitor lags the resistance by 90 degrees XC. And the capacitor reactance and the inductor reactance are out of phase by 180 degrees. And the reason why I've done reactances is because I'm going to use that for this question here. Normally it's introduced to you in terms of voltages, because that's what you normally would read off like an actual oscilloscope. You just read the voltages off the specific components. But all you do is divide all the voltages by the current, because the current is like, it doesn't go out of phase in terms of the components, because current's just an electron. So you can't have sort of, we'll leave it at that. It's the current's always in phase with the resistance. Right. Calculate the value of theta. So we know that the impedance leads, or the impedance is up here somewhere, because it leads the supply. So we have Z up here, and we have the resistance R. So we can actually work out the angle. So we've got we have R across here, That's R, and we have the impedance, which is Z. We have Z, and we're trying to find out. This would give us the we know that the reactance of the inductor is higher than the reactance of the capacitor because we're like up on the positive end of the spectrum. So if you remember that the total reactance is just the reactance of one of the inductor minus the capacitor, or the capacitor minus the inductor, it doesn't matter. It's just the magnitude. So VS impedance is a phasor diagram. Yeah, I hope so. I hope I get what I mean by that. So this is a phasor diagram. I've drawn the phases. So I've drawn this as a resistance. I've drawn the impedance. This angle here is theta, although normally in the textbooks it's given actually as phi. So yeah, this is VS impedance in a phasor group. I know what you mean. VS is the essentially. Well, I can see what you mean. If you got VS and divided it by the current, that would give you the impedance. Yes, I know what you mean by now. Yep. So we have a triangle essentially. We have 93 on the hypotenuse. We have 55 as a resistance, and then this is our right angle triangle. Super messy, but whatever. That's our angle. We're going to have the adjacent. We have the hypotenuse. We're going to use cos. So cos theta is equal to. Can I describe source voltage as a supply voltage? Yeah, they mean the same thing. Yeah. The adjacent, which is 55, divided by 93. So down here, the theta is equal to cos inverse of 55 divided by 93. And I'll quickly do that in my calculator. Note, when you're doing your exam, you will need to go shift, set up, and change 2 degrees. Because you probably would have done your mechanics exam first. Maybe, I don't know what order you're going to do it in. But you got to pay attention to that. Otherwise, you'll get a weird answer. Are phasor diagrams usually merit? Yes. Or excellence. They're never achieved. Not as far as I remember. I don't think I've ever come across phasor. No, they're not. They're never achieved. 93 bracket. Usually they're excellence. So we have a phase angle of 53.74, which is 53.7. So that is equal to 53.7 degrees. Right, show the reactance of the inductor at this frequency is 98.6. Cool. So we have the inductor. This is going to be omega L. We have the resistance. This is R. We have the capacitance, or we don't actually have the inductance. We're going to work that out. We have the reactance of the capacitor. Oops, that's not omega L. Oh, that is omega L, but I'm going to write XC instead. The XL, I should say. XL. I wrote the actual thing for it. And this is XC. All right, the value into the formula. So for the for mechanics calculator should be in radians, and for electricity it should be in degrees. Usually, for simple harmonic motion, you probably want to have things in degrees. It really depends on the question. If they're working in radians, then you want to be in radians. If they're working in degrees, then you want to be in degrees. That's pretty much the only thing I can sort of say about that. Because sometimes, like if you're writing a question as an examiner, you'll sometimes deliberately write a question to be like, I can throw these kids off by like doing things in degrees. And they will like would have had to calculate on radians. Probably not always, but it's kind of if you can be sneaky about it, you maybe give it a go. Hopefully that answered that question. What's the difference between impedance and reactance? So impedance is the sum of all the resistances. It's the sum of the resistance plus the reactance. Reactance is just the reactance of a capacitor or an inductor. So the impedance formula, which you need to memorize, we have Z squared is equal to R squared plus, and then we've got bracket. The order doesn't matter, so it could be the reactance of the inductor first or the reactance of the capacitor first. It's just the difference between the two. So we're going to have XL minus XC squared. And this comes about because of this vector diagram or this phasor diagram down here. They're not vectors, they're phasors. So we have the impedance Z up here. And we're trying to find out this value here first, because this value here is XL minus this minus XC. That should be XL, by the way, and that is XC. this side over here. So we'll quickly do that out. We'll work that out. So we're going to go z squared, because that's hypotenuse, minus r squared is going to be equal to, and we'll square root that as well, because it's Pythagoras' theorem. We're almost running out of time, not quite. Shift square root bracket. What was the impedance? Where is the impedance? 93 hertz, wasn't it? 93 squared minus 55 squared bracket equals. So we have. I've done that right, haven't I? We have it. There's fine. 74.99. Go away. 74.99 ohms. So we have X. We know that the inductor is bigger. The inductor reactance is bigger than the capacitor reactance because the impedance leads the supply. So we know XL has to be bigger because XL minus XC made the whole thing positive. Right, so we're going to have XL minus, and the reactance of the capacitor is 23.6. 23.6 is equal to 74.99. And you can see if you add these together, XL is equal to these things added together. And I'll quickly do this in my calculator just so I can check for myself. Plus 0.6 equals 98.59, which is 98.6. 98.6 ohms. Typically, okay, this will be excellent question. Guarantee it. Typically, it wouldn't be a show though. It would just be a calculate. So it's pretty uncommon that it's asked you to show that the reactance inductor this frequency is 98.6. It's typically just a straight up calculate question. So this would actually be quite difficult to get if you were doing this exam in 2013, simply because you'd sort of have to show all your working as you go, sort of like what I've done. And it pays to have these phasor diagrams here just so you can sort of orientate yourself. Explain what must be done to the supply frequency to bring the circuit to resonance. So the reactance of the inductor is dominating. So we need to drop that down. And by dropping that down, we just decrease the frequency. So I'm pretty sure, hopefully I pre-wrote this question. I did, good. At resonance, the reactance of the capacitor is obviously equal to the reactance of the inductor. That way their phases up and down. So the reactance of the inductor will obviously exactly cancel out with the reactance of the capacitor. We know that the reactance of the inductor must be greater than the reactance of the capacitor, and that's because the impedance leads to supply. You must decrease the frequency to bring it to resonance. When you decrease the frequency, the current of the circuit will hit maximum, and that's because now there's no reactance. Well, the reactance of the circuit is zero. There's still reactance. It's just the net reactance is zero. So all there is resistance. Cool. Why is reactance calculated using angular frequency? I don't know. It's probably a bit beyond the scope of, maybe you probably want to chuck into YouTube derivation of the reactance formula for capacitors and inductors. That's probably, I actually can't remember off the top of my head why it's 2 by F. I know that's directly related to it, but yeah, I actually don't know the exact relationship. Resonant frequency is 220 times 10, it's 220 hertz. Considering resonance condition or any other method, calculate the inductance of the inductor. So on your formula sheet, you'll have the formula for resonance. It is somewhere here. It's right here. There we go. And you can derive this by just setting XL equal to XC. So you can derive that formula by just going XL is equal to XC and then putting the formulas in for both of those, and then you can get to the resonant frequency circuit formula, but it's just easy to write out. So F is equal to 1 over 2 pi square root LC, and then all we're going to do is just rearrange this for L. So I'm going to rub this out so I can have some more space. 2 pi f is equal to 1 over square root LC, and then this is just equal to omega, so that's, we'll just put a line there. Omega, well, we're 1 over omega is equal to square root LC, and then we'll just quickly chuck a line under here and do the working down over here. So we'll square both sides, I should say. So 1 squared is just 1, so 1 over omega squared is equal to LC, and then we'll just move the capacitance underneath. So 1 over omega squared, and then we'll move that capacitance underneath. C is equal to the inductance. And we've got 4 minutes to go, so I'll skip out the working for that. But you can see like the angular frequency is just 2 pi f, and these times that by the capacitance, and that will give you the inductance. Right. Explain how the frequency of the supply can be altered to produce a short burst of sound from the speaker. This, in terms of like writing this question, is quite tricky. So if you look at the but normally when you tune like series LCR circuits and you're tuning for resonance, you're looking for maximum current. If you have parallel circuits, you're looking for maximum voltage, but not even worry about that. So you're looking for maximum current, and the graph of that with regards to frequency. So if we have frequency on the x-axis and the current on the y-axis, looks a little bit like this. So that's what it looks like. So as you get either side of it, then the current drops off dramatically. The caveat to this is if your resistance in your circuit, here we've got 55 ohms, which is quite small. If you have a massive resistor and then you have really small reactances, this graph isn't entirely true. In fact, the reactances of the capacitor and the inductor wouldn't actually do much to the circuit whatsoever. Normally, these questions have very low resistances, specifically so that the current can sort of be more dramatic, I guess. So what I'll put for the answer is the frequency can be swept from high to low. As the frequency moves through the resonant frequency, the reactance drops to 0. So all of a sudden you have no reactance. That's when you hit max current. And the current will reach maximum with impedance. Impedance is minimum. So now the impedance, Z, would just be equal to, well, it'll be equal to square root R squared plus the omega C minus omega L. Oh no, XC minus XL. I'm just getting this muddled up. XC minus XL. I was trying to write the formula instead. Squared. This here has gone to 0. So then we can just cancel that out completely. So now it's gone to 0. The impedance is just now the resistance. So this will maximize the power output and can cause a short burst. If you did this in reality, you probably wouldn't really notice that much of a short burst. It would only sort of be mild. It wouldn't be that dramatic. So yeah, so another type of question that you can ask for this is if you had a capacitor, and you could, like, I think there was one year where you were varying the dielectric, and it was asking what's more sensitive, the dielectric or the change in current, or I'd say change in current, which would be more sensitive, and it's a change in current by a large margin. So if you just, and that especially if the resistance in the circuit's quite low. So if you have like a 5 ohm resistor and you go from like 1 ohm of reactance to no ohm of reactance, you're going from 5 to 6 ohms, which will actually change your current by a reasonable amount. Whereas if you're changing your dielectric by maybe like 0.1 or 0.2, you're going to get a very, very small percentage change in the total capacitor. So yeah, so that's something to think about. Looking for current changes are far more dramatic than any other changes. Right, it's now pretty much 7 o'clock, so I think we'll call an end to this tutorial. If you do have any questions, just chuck them in the chat. If there's any like questions here that you were just unsure about, or these topics that you have no idea about, I would highly, highly encourage you to go to that first PowerPoint that I showed you and go to the questions where you can like practice the questions on specific topics. That's probably your best approach for now. Cool.
Awesome. Thank you very much, Andrew, and some great questions in the chat. Remember as well, because when we close this stream, the chat won't be active for much longer. You can, of course, jump over to Study It and ask any other questions there. All right, good luck for your exams, and if you're studying waves, then we'll see you back online shortly. Thanks, Andrew.
Okay, Dave.